within our seasonal school on network federated learning. We have the great pleasure to have Dr. Wojciech Samek from the Fraunhofer Heinrich Hertz Institute to teach us about communication efficient and personalized federated learning. Wojciech Samek is the head of the Department of Artificial Intelligence and Explainable AI group at the Fraunhofer Heinrich Hertz Institute in Berlin, Germany. He studied computer science in Berlin and Edinburgh and received a PhD degree with distinction from the Technical University in Berlin in 2014. He is associated faculty with several world-class institutes in the field of machine learning and AI. Moreover, he is the recipient of multiple Best Paper Awards, including the 2020 Pattern Recognition Best Paper Award. And he's also a member of the expert group developing federated learning related standards, ISO standards. He is also the leading editor of the Springer book, Explainable AI, Interpreting, Explaining, and Visualizing Deep Learning, and organizing various special sessions, workshops, and tutorials on topics related to explainable AI, neural network compression, and federated learning. So we are really amazed to have you, Wojciech. Take it away.
Yeah, thank you very much for this kind introduction, and thank you for the invitation. So let me share my slides. Yeah, so today I will talk about two topics, two directions we have been working on in the federated learning domain. One is like how to make federated learning more communication efficient, and the other topic is about personalization of federated learning solutions. So I will tell you what it means later on in the talk. So today we see settings where data is distributed. We have smartphones, IoT devices, billions of users, and also, like in other domains, hospitals have medical data, but are maybe not allowed to share it outside. And with this distributed settings, people have recently developed machine learning methods which can cope with this, so which can learn without centrally gathering the data. And this has advantages in terms of privacy, efficiency. You don't need to communicate your data forth and back. Security, so you don't have a single point of failure. And of course, also ownership. So people have full control over the data. They don't give it away. So therefore, like this distributed settings and federated learning settings are becoming more and more popular today. So we have a movement towards this distributed learning where deep learning models or machine learning models in general are running on a local device and are continuously learning, and these updates are kind of communicated either to a central server orchestrating this learning process, or in a peer-to-peer fashion, depending on the scenario. And this has, of course, these advantages as efficiency, privacy, full control, and from a theoretical or methodological point of view, it comes with very interesting new challenges. So to make federated learning work, we have many challenges. So for example, robustness, we need to take care that this learning works well, even if some of the participants are adversaries. We need to take care of the convergence. We need to deal with heterogeneous data. And also we need to deal with communication efficiency. If we naively implement this framework, we will require a lot of communication, and in many cases, this will be overwhelming. So we need to develop smart compression methods which reduce communication overhead, but still ensure that learning is performed. And we will also talk about it later. We need to take care of personalization, especially if we have data from different sources. This data may not only be heterogeneous, but also like the preferences in the data may be even opposing. So training one model may not be enough, and defining like personalizing the solutions towards groups of clients is one solution to this problem. But first, in the first part of the talk, I will present you and review some of the methods which have been developed for reducing the communication overhead. So here in our institute at Fraunhofer HHI, we have a lot of experience with compression methods. So my colleagues are developing compression standards for video coding standards, international video coding standards such as H.264, H.265, H.266. Yeah, we kind of are collaborating on developing also this kind of compression techniques for neural network compression, but also for reducing the communication overhead. So in this federated learning setting, we usually assume that we have a central server kind of controlling the learning process, and these local models are sent back and forth to the clients and to the server. So the clients are kind of getting a new model, learning locally, updating it, and sending it back to the server. The server is integrating these different local models and sends back a new updated model. And this process is repeated over and over. And each of these communication steps can be quite expensive. For instance, if you think about it, like how to kind of calculate the total communication costs. Basically, the total communications costs are a product of the communication rounds. So how often do you communicate with the server? Times the parameters. How many parameters do you send to the server and back? And the encoding of this parameter. So what is the average code word length of these parameters? And as we will see, by using some smart lossless coding techniques, you can even reduce the amount of bits you need to encode a parameter. And if you would do it like very naively, if you would just train BGG16 on ImageNet in this federated learning manner, and you would communicate every iteration until convergence, and you would send all the parameters every time and encode the parameters in 32-bit, you would need almost 500 terabytes of communication, just one client. And this is, of course, not a good idea. And people have developed smart techniques to reduce this overhead. And basically, these compression methods can reduce each of these factors. So you can use communication delay to reduce the number of communication rounds. You can use lossy compression techniques to reduce the number of parameters you need to communicate. And you may use efficient encoding of these parameters to reduce the average code word length of the information which you send. So communication delay is a very simple technique. So instead of like sending the graded updates like in distributed SGD, you aggregate, you do SGD for k steps on a local client, aggregate this information and send your delta parameter matrix to the server. And the server kind of averages it. And people show that in and by that, since you are not, since you are aggregating, you are doing multiple steps of SGD on the local client, you can save a lot of communication. And this works and converges in many cases. So it's the advantages is it's simple, it reduces communication frequency, especially if you do federated learning on device, it has advantages. It also reduces both upstream and downstream communication and is easy to integrate with privacy mechanisms. But on the downside, it can affect convergence speed drastically, especially if data is heterogeneous. So with increasing heterogeneity in the data, convergence speed drastically decreases. So you can see here on the right, for 5 epochs training with different with data sampled with different Dirichlet parameters, so with increasing heterogeneity, and you see that after 5 epochs, if the data is IID, so on the left side, you have a quite good performance, but if the data becomes more and more heterogeneous, the performance or the convergence is much slower. And this effect aggregates if the number of participating clients is low. So this can be put on the downside. So communication delay is a great trick, but it has bad performance if the data is heterogeneous, and it has some kind of low sample efficiency. But it's still a good, in many cases, still a good idea to use it. Yeah, and if you think about, like, as I said, you can not only reduce the communication route, but also like reduce the parameters communicated. And what can be done here is just to introduce some compression factors or compression functions. So for example, here on the right, you perform distributed SGD, but with a compression applied to the gradient. And depending on the compression, you can reduce the number of parameters quite a lot. And there are different compression schemes have been proposed. So if you see, like on the left, this would be, for example, your gradient without any compression. And people propose, for example, to just approximate this matrix just communicating the sign of the values, or just communicating the top k largest numbers or smallest numbers, or use some sparse randomization, and convert this matrix into a ternary gradient matrix, where you just have like the top largest and smallest, and also like a lot of zeros. And some of these compression functions are biased, some of them are unbiased, and as people have found out that, like, if you just use the unbiased compression, then convergence analysis becomes very easy. So you can prove convergence. So even if you're not sending the gradient as is, but if you send the compressed version of the gradient, you can still prove convergence. However, in practice, this unbiased compression schemes work less good than the biased ones. The variance blows up, so they have poor empirical performance. And yeah, so here you see like the definition of the biased compression operator. So the expected value, if you apply it on your vector or matrix X, is not equal to to X. So you introduce a bias, and if you just apply it to what we saw here, just apply a bias compression operator to your gradients, convergence is not guaranteed. So which seems like a bad thing, because of course convergence is necessary and is highly important for this distributed learning. But there is a cool trick introduced in the work of Kari Reddy and Stich, and they showed that you can turn this bias compression methods into a convergent method via error accumulation. So you can introduce error accumulation and make these updates converge. So what does it mean? So it basically means that you locally track the error you make and you kind of add it to the next round. So since you are not communicating the true gradient, but a compressed version of it, you make an error. And this error you should track and aggregate, accumulate locally. And by accumulating it, you kind of avoid error propagation, and you can show that this guarantees convergence. So this is something which is, I think, a really good thing, because you can turn a non-converging method into a converging one. And yeah, and this is just a summary of what I said. So there was like this unbiased compression methods which have where you can prove convergence. There's a bias compression techniques which work better in practice, and where people showed that you can also prove convergence when you adding this accumulation trick. And in our work, which was published 2019, so it was a while ago, we kind of tried to best combine these different tricks to get the best of all the three factors. So we tried to reduce the communication by reducing the communication rounds, by reducing the parameters, and by reducing the average code word length. And we showed that this gives very good results. And one thing which we did is just adding this delay communication in this very simple fashion. This gives a factor of 100 to 1000 in compression, because you are not communicating that often. We then also use some sparsity operator. So like in principle, the one which you saw here, that we just communicated the top K, largest and smallest. And we even further reduced this communication, this communicated information by binarizing. So we kind of among the ones which are among the K largest and smallest ones, we kind of decided for the largest or the smallest one, and just communicated one value. I will show you in the next slide how this works. And we even showed that you can, since what you communicate is very sparse, you can encode it via column coding and gain an additional factor of compression. And here is like a simple example. So what we assume you want to communicate this delta W matrix, or vector in this case, which is our kind of aggregated gradient of the delta and the parameters. And you apply first the top K operator. So assume you identify from these vectors the two largest and two smallest elements. What you do then is to identify, or like to average them. So just say, okay, what is on average, are the positive ones by magnitude larger than the negative ones, which is in this case is the case. So in this case, you kind of binarize. So you decide to just send the positive largest k parameters, but you just send the mean value. So you don't. So in principle, you would send the 4 and the 2, which is on the 3rd and 4th position of the vector, but you just send the mean value. So in the end, you send one value and 2 positions where this value occurs, and everything else is 0. So the vector which you send is very, very small. And from like compression literature, it's clear that for large vectors, it's often more better to not send the position directly, but to encode them as distances between non-zero elements. So you encode, you send, okay, where is the first non-zero element, and then the distance to the next non-zero element, and this you encode via Gallam coding, and aggregates the errors with the error accumulation, which I introduced before. And this gives you a large factor in compression. So you, compared to just federated averaging or to the naive baseline, you get a large factor, a much better compression without drop in accuracy. So even compared like to federated averaging, this gives you a lot of advantage. And this we did first for data which is more or less IID distributed, and then we extended it and had to work about how to introduce it in heterogeneous settings and like more real life federated learning setting. And in the heterogeneous setting, you kind of can skip this communication delay, or you can reduce it, because otherwise this would slow down the convergence. And what we also introduced is an upstream and downstream compression, so you can do the same specification tricks which you do in the upstream. You could also do it in the downstream. You would then need to locally track, locally accumulate the error which you make, not only on the clients, but also on the server. And of course, what you always can do is partial participation of the clients. And with that, you get, even in non-IID settings, you get a large, much faster convergence and better results. So on the left, you see like the sparse canary approach, which we propose, and compared to federated averaging. If you have a fixed number of graded evaluations, we get much higher accuracy. In the IID and non-IID setting, on the right, you fix the target accuracy and compare the megabyte which you need to communicate. And also here you see that to reach accuracy, you need to communicate much less. So a smart combination of these communication delays, specification, encoding tricks, you can get very good reduction in communication overhead. And recently, we also thought about communication efficiency on a very new federated learning scheme called Federator Distillation. So compared to federated averaging, where you kind of aggregate, where you directly communicate the models, the parameters or the deltas, and average them on the server, in federated distillation, the knowledge is computed in an indirect manner. So what you do is assume that you have like the server communicates kind of the model to the local clients. So they have some initial model, then they train. And what they do is they do not communicate the deltas, but they apply the model to a public data set and communicate the prediction scores on this data set, so the outputs. So you do not communicate the parameters, but you communicate the kind of the outputs, the predictions on a publicly available data set, and this data set is available to all the clients. And what the server then does is the server aggregates these predictions and use distilling to distill a new updated model. So, in this setting, what you could also do is the server aggregates this local predictions, then sends these local predictions back to the clients, and the client distills their new updated local model. And the advantage is here that you can perform federated learning even if the clients have different architectures, because you are not directly averaging parameters on the architecture of your model, but you kind of communicate outputs on a public data set. So client 1 can have a different neural network than client 2, and then client 3, and so on. So this is a very nice property of this approach. And we thought about like how can we reduce the communication overhead here, because the communication overhead depends on the size of the distillation data set. So the more samples you have on the distillation data set, the more values you need to communicate. It also depends on the entropy of the soft labels, so on the thing which you communicate, and also on how you encode it. So if you encode it in 32 bits, then maybe you're not the most efficient. So what we did is we kind of introduced a quantization and a delta coding technique. I will not go too much into detail here, but the basic idea is that we have like our outputs, our predictions, and we just represent them as a one hot encoding vector. So we just send the argmax of P, so the highest vote. So assume this is like a classification task. This would be like the most probable class. So you just represent these vectors which you communicate in a very sparse manner, just a lot of zeros and just one. And this is sent around. And we apply some trick delta coding, which kind of also uses this temporal, you kind of locally track this temporal dependencies. So if you send this vector in this round, and things are not changed, you do not need to send the same vector again, but you kind of you only send the thing which have changed compared to the last communication step. And with that, we can reduce communication quite a lot. So here you can see, for example, in VGG, or ResNet with the highest target accuracy. And we compared like for IID data, non-IID data. And you see that federated averaging needs a lot of communication. Federated distillation, as implemented in a standard fashion, reduces this amount quite a lot. But our coding techniques further reduce this communicated information by another large factor. So we can train these models in a very efficient manner in this way. Of course, the price to pay in this setting is that you need this distillation. So this distillation also requires local computation. So if you would do it on a smartphone, or mobile device, this would not be the best way, because you would require a lot of local computation every time. You would need a distillation step, which is computation heavy. So depending on the scenario, federated averaging or federated distillation may work better.
There's one question regarding these numbers. Which platform is employed for these experiments? I don't know what is meant by platform here.
I mean, we had our first, I mean, we just we had like a Python implementation and simulated this learning on a server, but we didn't. I mean, this was just like experiments which we did on our server with these models and the data. So these are not really like mobile communication experiments. There was not real hardware. Like the clients were all running on one computer, kind of.
Did you use PySwift or Fate or similar?
I think, as far as I remember, we implemented our own framework.
Okay, thank you.
So this was like the first part on the communication efficiency. So as you saw, there is a lot of you can do about reducing communication. I know that this field has been also like quite active, and a lot of approaches have been proposed, and depending on the scenario, a combination of some of these methods may be good, or another combination could be better. So it really also depends on the requirements which you have. But here is the second topic of my talk, personalization and federated learning, because until now, we kind of have assumed that we have one model which kind of does the job. But federated learning environments are characterized by a high degree of statistical heterogeneity of the client data, which means that the client data may be very different. Also, the client behaviors may be very different. And it may not be a good idea to have one model for all. Here you see like on a more abstract level. So what we have a distribution of clients data in the label. And if you assume that the distribution pi y given x is shared, so if you assume that all clients have the same preferences, that they does the thing in the same way, you can fit one model. So for instance, you could, if the task would be digit classification, and the clients would have MNIST digits, but the one client would have just one digit and the other one would have another digit, this data would be non-IID, because like this P of X of the clients would vary. But there would be one model which could solve the task, because for every client, this classification would work the same. But in some situations, it may be the case that the clients cannot agree on this model P y given X. For instance, if you would classify preferences or attractivity scores on images, maybe some clients like people with glasses, but other don't find them attractive, or some clients find this kind of music and other clients don't like this kind of music and like prefer other music. So in this setting, like training one model would not solve and satisfy all clients. So here you see, if you would have a server and some clients like classic music but don't like heavy metal and techno, they wouldn't like to have a preference predictor as another group of clients which are more into electronic music. So the solution would be to train one separate model for each cluster. If you would use this cluster structure, you could train one model for each cluster, and this would be like a personalized model or cluster specific model, which would capture the preferences of these clients. But the problem in federated learning is that the server doesn't have a clue about the preferences of the clients because the server doesn't have access to the data. So the question is how to identify these clusters. And we found a solution. I will briefly tell you how it works. So assume that you have two clusters. You have two clusters, and in each cluster, you would have a local empirical risk, which you would like to minimize, right? So this is kind of the, if you train a machine learning model, you would typically minimize this risk function, which is Ri in our case. And like G and H are kind of these two clusters. So if you jointly train, you minimize the overall objective. So you minimize the sum of this local empirical risk functions because you optimize like one minimum. And here, like this parameter CI and 1 minus CI is just like the kind of the size of the cluster, how many data points are inside this cluster. And assume you have trained your federated learning model. So you arrive at the local optimum. So the gradient of this function f is 0. But what does it mean for the gradients of these cluster-specific functions G and H? In the one case, they could be also 0. In this case, you would be done, because in this case, these clusters would have the same preference. So you would arrive at the same minimum for both clusters, for both groups. This would be the case that everything is happy and everything works out. But in the other case, this gradient of f can be 0 if the gradient of f is kind of opposing the gradient of h. In this case, they have divergent preferences. So I will show you here like a plot. So this is like in parameter space. So you start with a parameter phi 0, and you kind of compute this local gradients. At every local client, you compute gradients, and you kind of the server aggregates them and moves towards the minimum. But you are moving toward a minimum which is between the minima of these two functions, of these two clusters. So you are not moving in the minima. You are not reaching the minimum of the one, and you are not reaching the minimum of the other one, because in this case you have opposing preferences. So you cannot train a model which satisfies both groups at the same time. But as you see, the property which you get if you arrive at the minimum, the property which you have is that say the directions to the cluster, to the red cluster and the blue cluster, they are opposing. So the gradients are opposing, which you can, or they are kind of 180 degree, which you can note as, or which you can kind of capture as a, if you would compute the cosine angle between this red and blue gradients at the minimum which you reach after federated learning, you would see that the cosine angle is kind of -1, so they are opposing. And you can use this fact. You can use this fact to compute the similarity between these groups, to learn about the cluster structure without seeing the data. So in principle, what you just need to compute the cosine similarity between the gradients at the point where federated learning converges. So if you converge, you compute the cosine similarity between the gradients, and then you know whether you have one solution for all, whether everything is fine, or whether you have opposing preferences. So in principle, what we do is we compute like this alpha ij similarity or cosine similarity values between all gradients, all clients in this case, and use this as a criterion to split the client group. So I will show you like how kind of this works. So you start training with all clients, until convergence, and then you compute these cosine similarities. And what you then see is that one group of clients has kind of opposing cosine gradient directions than the other group. So you are splitting this group into two parts, and then you are continue training with two different models, so one for each group, and you do the same until convergence, and then you are seeing whether you should split again or not. And in the lower group, in the blue group, you do not need to split again because they have the same preferences. But in the other one, you also find groups of clients with opposing preferences, so where the cosine similarity is close to -1. So you split again and train again. And by that, you get a personalized solution for every group. So you don't need to pre-specify this group structure, but you learn it kind of on the fly by splitting. And we have also a theorem, a separation theorem, which kind of proves that you get the correct splitting. You get the correct splitting if your gamma is small enough. And the gamma tells you how close is the empirical risk from the true risk, from the true minimum. In some senses, gamma, of course, depends on the number of data point of samples, on the difficulty of the problem, but in most cases, we have seen this condition is fulfilled. And if you have enough samples, if you have enough data which support, so if the problem is learnable, because in all machine learning tasks, you assume that your empirical risk is close to the true risk, because this is what you want to optimize. You want to optimize the generalization performance, and this is kind of the implicit assumption that your empirical risk, which you kind of measure, is a good approximation, a proxy of your true risk. And if this is correct, then we can show that this method gives you the correct clustering. So we also simulated it. Above, you see like depending on this value of gamma, you get like a provable correct clustering. You get a clustering which is very probably correct, and you get clusterings which are not correct because you are too far away from the true risk. So this is the idea of this clustered federated learning. So again, you kind of start training with all clients, and then after converging, you kind of measure these angles, and you try to find a split. You've tried to find a split into two subgroups. This is a selection criteria. You try to split these client groups into a group C1 and C2, depending on the similarity values. So the similarity values are just kind of the cosine between the gradients. And once you split, you continue training with each where you have like a separate model for every group. And after convergence, you see if you can split again or not, and you do it like all over until you arrive at a solution which kind of works for all. This is the idea of clustered federated learning. And with that, you can train with all clients, and you can find a solution where you have a model specializing in learning the preferences of the one group, and another model specializing in having preferences of the other group. And the cool thing is that you do not need to predefine this cluster structure, and also on the way you kind of use the knowledge of the other groups. So because in learning, as all we know, at the beginning, often like you learn like maybe low-level feature. If you train a model which on image classification, at the beginning it always learns simple low-level image features, which may be good for all groups. But after some time, you kind of specialize, and then you split. So this is like an approach which works well here. And we also applied it to identifying adversaries. So because you could say, okay, maybe I have a group of benign clients which behave similarly because they are benign, they are good. And you have some clients which are adversaries. So they do something wrong, or on purpose or not on purpose. They have some noisy labels or some label flips. And what we wanted to know is whether we can identify this different subgroup. So it's kind of like an outlier detection during training. And once we have identified them, we can remove it. We can kind of discard them from the training. And similar to like you would detect outlier and remove them from your data, we are detecting adversaries in federated learning and removing them. And as you see, in different settings, we get very good results, where like simple federated learning fails. So this was the second part. So I would like to close with a few words about this new MPEG standard, which I'm co-developing. So NCC, Neural Network Compression Standard, developed by MPEG, yeah, it's an ISO IEC standard, MPEG 7 part 17, and it is developed as a toolbox. So it works with different frameworks and networks formats, and it gives you kind of a semantics, but also like a coding tools, coding methods, and we can get high compression efficiency without degrading classification performance. And the standard was developed for compressing neural networks. So it has like some pruning methods, classification, also quantization techniques, and entropy coding, a smart entropy coding, which we kind of took from the video compression community and adapted it to neural network compression. And currently, this kind of standard is finished for neural network compression, is kind of ready. And currently, MPEG is working on an update on incremental compression of neural networks. So whereas the original standard was focusing on how to compress our models as they are, here we are also including federated learning use cases where you want to compress updates of models and maybe iterative updates. You also have this temporal dimension. And yeah, we have this initiative has started like last year, and we have now we are currently like finalizing the standard and on this extension, and it will also be available soon. So concluding, so federated learning is a very powerful training scheme. It has a lot of advantages for distributed data. Cluster federated learning allows to apply federated learning in realistic scenarios where clients have diverging preferences. So it kind of it removes this very strict assumptions that everybody has the same preference. And many challenges still exist: robustness issues, complexity issues. And yeah, this new MPEG standards will also hopefully we took also up by the industry and allow interoperable and very efficient implementations of federated learning in the future. So with that, I would like to close. Here are some references of the things which I talked about. And we have also websites where all these papers are available. So yeah, and I'm very happy to take questions. Thank you.
Thanks a lot, Wojciech, for this excellent talk. So we got some questions on the chat. I might work backwards because the most recent ones might be regarding the latest slides. So first question would be, how can we handle personalization in non-stationary or real-time data? So how did you look at the dynamic settings for this clustered federated learning methods?
We looked at the cases of non-IID-ness because, yeah, I mean, this is a bit tricky because you have to decide at some point whether like these clients differ in preferences or whether they just have different data. Like you have to decide between the non-IID data case where one model could be fit in principle and the case where no single model exists. And we have found a solution for that. So we kind of discuss this very detailed in our paper. So we have like what you kind of need is two thresholds. One threshold determines when to split. So if the similarity is below a threshold, you would split, and the other threshold kind of takes care of the case to distinguish the situation between IID case and the case where no model is can be fit, because so it's a bit tricky to explain it now in detail, but we took care of it in the paper, and we also discussed it and also made some experiments and showed that this can be handled. But of course, in a dynamic setting where things are more complex, and this may become a problem at some point, right? This is always with outlier detection. I think it's always problematic to see what is an outlier and what is new information which you have not seen yet, but which is not an outlier. So this is, I think, is basic problem which we will not be able to solve fully, but depending on the application, you can define certain constraints to make it practical.
Yep. Then there was another comment. So in principle, as I understood, these similarities, cosine similarities, you could just use as a similarity measure as an input to any clustering algorithm that accepts similarities between two data points. So did you try out like agglomerative or hierarchical clustering methods?
I think you could. I mean, we didn't do it because, I mean, our separation theorem kind of works for this binary splitting. So we kind of proved that when always like using this binary split, you arrive at the correct solution. But you could, in principle, try to take the similarity scores and find multiple clusters in one step, but then we would maybe lose some of the theoretical guarantees. But or maybe one could extend this proof to other clustering methods. This we haven't looked at it.
And how does this two-cluster setup relate to the goal of detecting adversaries or attacks? So how are these adversaries characterized? Are these small clusters?
Yes, yeah, they are characterized as a minority cluster, yes.
Yeah, very good. Then what else do we have here? How are the preferences defined when running the simulation? I'm not sure what is meant here by preferences, but I guess, yeah, these cosine similarities, they are not known beforehand. These are updated as you train the models.
Yes, yes. I called it preferences, but in principle, it's like this distributions Pi y given x. So this is like this conditional distributions which you want to, which I defined as preferences, but you don't know them beforehand. Yes.
Yes. Then one question from earlier on, now finally pick it up. Sorry for the delay to the student or participant. So the question was, is federated distillation or this distilled federated learning the main goal to reduce the communication?
I don't think so. I mean, there's one key advantage of this is that you can train models with different architectures. So this is, I think, a very cool feature, because you are not restricted to having models having the same architecture.
Yeah.
So this is one key advantage of it, and this communication thing comes on top of it. But as I said, maybe the downside is that you need more computation. So you reduce communication, but you trade it off, and things become more complicated. But but this architecture thing, I think, is unique and is very, very cool.
Yeah. So instead of sharing model parameter updates or model parameters, which require that all models have the same format, the same vector size, for example, you now share some form of raw data, or not raw data, but simulated data. You
share not the models, but the behavior on the model on some data set which you define. So
this
you can So it's more like an indirect knowledge about the model.
Yeah, and in this way you make it model independent in some sense.
Yes.
Very cool. So you could, for example, some nodes use neural networks, other nodes use decision trees.
Yes, in principle, yes.
Yeah, very good. So there was another question. Yeah, but related to this question, also that question that I had, did you look at lower bounds? So I like information theoretic lower bounds that tell you cannot get more compression rate than what you already see in your experiments.
Yeah, I mean there is certainly like and entropy gives you like this type of lower bounds, but I think it's difficult to compute these lower bounds, because you have like a dynamic behavior. So you're not like you're communicating once, but you have multiple runs of communication, and of course these runs are not independent. So what you communicate now depends also on what you communicated in the previous round. So this makes it very hard to compute like the proper lower bound. But I think this is still a good idea to try to approximate it somehow. But theoretically, I think it's clear like what is the lower bound, but computing it may be difficult.
Yes, these lower bounds might need you need to assume some probabilistic model of everything, which might not be accurate actually. But when you shown this impressive compression rate numbers like 30,000 or what, I was wondering, how can we know how far are we away from really the wall? So is this?
But I think this is a very difficult question, because it somehow also touches to this minimum description length principle. That's what is learning, how much information you need to learn, what is kind of the optimum. Okay, here you use a fixed model, but you could, if you would extend this, you would, I think, arrive at this minimum description length theory, where we would say, okay, in order to learn to solve this task, I need this minimum, this type of bits to communicate.
Yeah. Okay, let me see. There's another comment, having the clusters does not contradict the federated learning. No, it's kind of a federated learning in the sense of pooling data sets in the same, that have similar statistical properties. So it's one more advanced form of federated learning. Sorry, I know I answered the question already. Then maybe the last question now that I take, if I would apply compression to traditional SVM, KNN, or decision tree models, what happens to accuracy?
I mean, you probably refer to this MPEG standard. I mean, you can certainly, some of the things you could certainly compress. I mean, quantization is one thing which I guess would also work with other more traditional model. So depending on how much bits you need to represent a parameter, if you would reduce it by some values, if you would have a smart quantization, you would certainly be able to to perform still well. This entropy coding is lossless, so it can be certainly applied because it doesn't destroy accuracy. It's a lossless coding technique, which kind of uses some kind of dependencies to encode it in a very efficient manner. It's an arithmetic coding. So I guess some of them you can certainly apply to more standard machine learning models.
Yeah. Okay. Yeah, let me wrap up. Thanks a lot again, Wojciech, for this excellent overview of the state of the art. Yeah, if there are no further questions, I highly encourage you to reach out to the presenter directly, and I will share the recording now with the participants. And if you would forward me your slides, so I could also share them with the participants.
Sure.
Yes.
Yeah,
Thanks a lot again.
Thank you. Bye-bye.
Bye-bye.